All right, so what about over here on the other side? So we could say, well, look here. We have x, and we've got this linear chain going back to theta. So you could say, we don't really need kappa. We just got, p of x given theta. There's nothing else connecting straight to kappa, right? There's no other observable that's cutting in here and connecting to the same thing. So the coupling is only through theta. So why bother with these intermediates? Just go straight from theta to x, theta to s. There is some value to that idea in the sense that we're not screwing with the connectivity of our random variables, right? It's just x is connected to s through theta. That's what this picture is telling us. There is, however, one effect that argues strongly for keeping kappa and lambda in the information graph structure. And that is, when you look at the actual expression for p of x given theta, in other words, where we've eliminated kappa from the picture, what you can see is that we haven't actually eliminated kappa from the picture. In other words, why are there 3 peaks here? Because there's 3 possible values of kappa. That's what we're seeing is we're just seeing kappa again, even though we got rid of it, it's still there. So I would say, again, this is sort of a situation like the first one that I talked about, that we can try to pretend that kappa is not there by drawing an information graph structure that hides it. But all that's doing is it's sweeping kappa under the rug. It's still in there if you look at the likelihood functions. So don't hide it under the rug. Keep it in the information graph picture. One way of stating that idea is what I would call the single peak likelihood rule, which is basically that a model should be like 1 peak. It shouldn't be, the model for x given theta is this funny 3-peaked thingy. Well, where do the 3 peaks come from? Well, actually, those are 3 different models that we're just pretending are one model. So under this single peak rule, we basically say the principle is 1 edge equals 1 likelihood model, which equals 1 peak. So if you follow that model, it's basically a way of saying don't try to hide complexity under the carpet by sweeping a whole bunch of things and pretending that they're one thing. Okay? And for me, this is a really useful idea because, it sort of keeps us honest, is one way of saying it. That the picture of the information graph structure that you show somebody really is a picture of the full complexity of the model. It's not like we're taking some arbitrarily complex structure, squishing it down so it looks like just one edge, and we're hiding all that complexity so that when you look at the information graph structure, you can't see, oh, there's actually all this complexity in there, but we're just not telling you about it. The person that this helps in general is you, the person who's building models and trying to come up with the right model. If I try to jump straight from theta to x, it's much harder for me to just automatically figure out, what the right weightings are going to be for all this, because it's really a function of the fact that there are these extra things inside, namely kappa. I can figure out the connection from theta to kappa. I can get that likelihood, and I can get the connection from kappa to x. Again, that's a clear model to me. But if I try to jump all the way from theta to x, then I lose track of details and my head explodes and I get things wrong. So strongly recommended to don't hide things under the rug. Keep the information graph structure as a clear, complete picture of what the complexity of your model actually is. Any questions about this principle? Okay, why don't we take a 5-minute break and resume at 1 o'clock.